We are in the midst of module number 6, which is all about spread spectrum techniques. And let's go and switch over to that. Okay, cool. Yeah, so the two main flavors were frequency hopping spread spectrum, FHSS, and direct sequence spread spectrum. We talked mostly about FHSS last time, and it has some advantages, some disadvantages. In particular, it was among all of the other nice things about spread spectrum techniques is they are quite resistant to jamming. And so I thought, I can't believe I didn't think to share this on Friday, but I have a historical video to share with you, which is why I asked about the computer audio. So it's a short clip, and it's from a nonfiction film. And let's see if we can share it. Okay, I hope you enjoyed that. A long time, what is it? A long time ago in a galaxy far, far away. So there's always something to be learned. So we left off on Friday with this slide, and that was the introduction of the alternative to FHSS, which was direct sequence spread spectrum. And so actually they're very similar. But the nice thing about DSSS is that we're not married to frequencies that we're hopping between. We are doing what has the same effect, that is spreading out the spectrum in the frequency domain, but you'll note that we are not using a frequency synthesizer, and we are actually free to use other forms of modulation other than FSK. So just because it's easy to not see the difference, if I can switch between the two slides. In here, if you're doing FHSS, you have to start with FSK modulation. It doesn't work any other way. If you choose to do DSSS, you can use whatever kind of digital modulation you like. In this particular example, it's a QAM modulator. But the idea is that we're not directly synthesizing frequencies. We are doing a multiplication in the time domain between the whatever baseband digital modulation signal you have and what's called the code or the chipping sequence C of T. Okay. But at its heart, C of T is a pseudo-random sequence. And so instead of mapping those pseudo-random numbers to discrete frequencies and then hopping to those frequencies, we just use the pseudo-random numbers to generate a chipping sequence, which is a sequence of ones and zeros, sorry, negative ones and positive ones. And then we map that to this C of T, which we then multiply to our baseband signal. Okay, so this is still, PN is still Pseudonoise. So it's a randomness introduced by a computer. The C of T is going to be either a +1 or a -1, depending on the pseudonoise, depending on the random input. And these are going to last, so each chip lasts TC seconds. And so again, we have short codes and long codes, just like before. I guess we called it fast hopping and slow hopping before. So now a short code is one in which TC is much less than the symbol period, and a long code is the reverse, where the chipping period is much greater than the symbol period. And we again use the factor of L to say how many chips per symbol or how many symbols per chip, if you like. So most of the time, I'm going to focus on short codes. We'll talk a little bit about long codes at the very end, but we'll say that there are L times TC chips in every symbol. So again, capital L is called the spreading factor. Okay, so let's do a quick little bit of algebra here. So the direct sequence signal, S sub ds, is the baseband signal, in this case QAM, multiplied by the chipping signal, which means that in the frequency domain, we've got the, well, I mean, we turn multiplication into convolution. That's not news to anyone here. But in particular, if I'm convolving two signals, then I add their bandwidths. So the immediate conclusion I want you to see is that the bandwidth of the direct sequence signal is equal to the bandwidth of the QAM signal added to the bandwidth of the chipping signal. Right? And that's a result that maybe you learned about called the duration property. Is that the duration of two finite duration signals, if you convolve them, you add those and you get the duration of the resulting convolution. And if you just map the word duration to bandwidth, the same property holds in the frequency domain. Okay. And there are a couple of abstractions here. In particular, I don't think we are showing mixing to passband. So that would be done before and after the RF channel. But the idea is we're going to try and abstract away from that and just try to work in the baseband here. Okay. Questions so far? Alvin, is that a question?
I accidentally unmuted my mic. My bad.
Oh, no. All right. So let's talk a little bit deeper about pseudonoise. We mentioned this a little bit on Friday, but the key here is that, sorry to flip back and forth, is in both of these architectures, both the transmit and the receive, is this box and this box need to be synchronized. And so this is where, if you're used to thinking of pseudonoise as purely random, you're going to run into trouble, because how do you ensure that two disparate computers come up with the same set of random numbers? And if you use the word random in there, that is a ridiculous proposition. But if you use pseudonoise, then it becomes a little bit easier to talk about. So if you have ever played around with a random number generator on your computer, there are many of them that give you the option to specify the seed of the random number generator. And so this is the way that if you have a random number generator, if you set the seed, then you'll get a sequence of random numbers. But if you and I are using the same random number generator, and we use the same seed, these on their own appear random. I'll put a squiggle there, but these will be the same sequence. Okay, so viewed on their own, right? If you cover up one of these branches and looked at the output, it would appear, as long as it was a reasonably good RNG, it would appear that they would be a random sequence of numbers. But if you share the same seed, then two RNGs that are physically separate can be built to output the same set of numbers. And so that's what we're going to use in our transmit and receive pseudonoise sources. Is we're going to have to somehow negotiate what the seed is, and then once the seed is set, then both of those PN sequences are going to be identical. most of the time, you would like your sequence of random numbers, your pseudo-random numbers, to have a very long period. The longer the period, the more random it's going to appear to be if you look at it for any given length of time. We're trying to mimic true natural random noise, and so we're trying to generate a sequence whose autocorrelation should be white noise-ish, if you like. And so remember, the autocorrelation of white noise is going to be kind of impulsive around 0 and then close to 0 elsewhere. Right. We'd like to, once we have shifted the pseudo-noise sequence by any number of samples, we'd like there to be very little correlation between the signal and itself. But you're never going to get away from the fact that if you don't shift it at all, you're going to get a spike there in your similarity measure. And then the cross correlations, what we're talking about here is if I have seed 1 producing a pseudo-noise sequence 1 and seed 2 producing pseudo-noise sequence 2, as long as these two are different, I would like the cross correlation to be near 0 between these two pseudo-noise sequences. That way, we don't accidentally see one noise sequence in another. So these are all things to look for when you're shopping for a pseudo-noise or a random number generator. So if you are in a bind, you can create a pseudo-noise sequence out of what are they called? Maximum length shift registers. Quick question here. You've obviously talked about shift registers in CPE, I don't know what, 133, your introductory CPE class. I guess I say obviously. Is that true?
Yeah.
So yeah.
Okay. So then have you also talked about these maximum length shift registers?
I do not recall that.
Okay. So the maximum length in the name refers to the maximum theoretical number of samples you can have before the sequence repeats itself. So if we do a little bit of arithmetic on, say, a length, what's this, a length 6 shift register. So in this case, M would be 6. 1, 2, 3, 4, 5, 6. If you set up your architecture in this way, where you're drawing out the first and the last bit, then the time, the number of samples between repetitions is going to be 2 to the m minus 1. And so this is the longest length you could have between repetitions. Max length, or really what we're talking about is max period. Okay, so let's actually make this concrete and let's do a quick demo. Let's make it slightly interesting. So what I'm going to do is I'm going to populate this shift register with a seed. So this is what I was talking about. Let's say we seed this system with the following values. And that means that we are going to, at time equals 0, so at n equals 0, we're going to pop out the 1. And then we're going to XOR the 1 at the end with the 1 at the beginning. Are you comfortable with, this is like a wraparound addition. So 1 binary add 1 gets us back to 0. It's the same as logical XOR. And so what ends up happening here is the 1 XOR 1 becomes a 0. I'm going to need an eraser here. But the shift shifts us down, so this becomes our 1. and then this becomes this, and the 1 gets popped off. Okay, so then at n equals 1, we are outputting 0, and then we're doing XOR between 0 and 0, which we again get 0, and then the shift register continues. So 0, 0, 1, etc., etc., dot, 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 until the 1 comes to the end. We get the 1 down here, and then we will, so I'll illustrate that. Eventually, the 1 that started at the head is going to get to the tail. And up until that point, we've been XORing 0 with 0, so we still populate with zeros. And then now, this 1 comes out to here, and now all of a sudden, we're doing 1 XOR 0, and so we get a 1 here and a 0 there. And so then this keeps going. And what we'd have to do is you have to do this for 2 to the 6 minus 1 before you would recover the same seed in the shift register. And then, of course, it would have to repeat itself. Because if you're starting from the same seed, then you're going to eventually get the same answer. Because this is, like I said, this is a deterministic system. The only quote-unquote random thing about it was what seed I picked. Okay, so the output of the maximum length shift register is going to be a sequence of bits. What we have to do to map those bits to codes, short codes or long codes, is to have a 1 go to a 1 and a 0 go to a -1. So if a 1 becomes a 1 and a 0 becomes a -1, then this is going to be your C of t. And so the cool thing about the codes generated by maximum length shift registers is that they have these autocorrelation functions that, if you squint, they look kind of impulsy, right? So they have to be periodic because the signal itself is periodic. But as the chip period diminishes, this thing gets narrower and this thing gets nice and flat. Okay. So they've got that going for them. Questions so far?
Wait, question.
Mm-hmm.
When you're mapping the ones, the positive one, and the zeros and negative ones, the ones and zeros that you have is that the output or the output of the XOR?
In blue, I have, so yeah, this arrowhead actually is kind of confusing. So let me try and modify this as best I can. This bit gets copied into 2 places. It gets copied to there and it gets copied to there, and we say it gets copied simultaneously. So the last bit in the shift register is outputted into this sequence, which is then going to be scaled and shifted to be +1s and -1s. But the bit itself, so in this case, the 0 would fly back here into the XOR.
Gotcha. Okay, so the blue that you're writing, it refers to the output, or basically that bit.
Yeah, everything here in blue you can think of as a binary system. And then when we get into the red, that's when we get to, I mean, technically it's a binary 0 and negative, or sorry, 1 and positive. Oh my God. Technically it's binary, 1 and -1, but these are going to be mapped to actual waveforms. So +1 rectangles, -1 rectangles.
Gotcha. All right, thanks, Clay.
Yeah, good question. And I think we can see that here. Yeah. So we've got, draw the 0 volt line here. Your spreading code is going to be, like I said, it's binary. It only takes 2 values, but it's important that it takes +1 and -1 rather than 1 and 0. And why it's important that it do that, I think will be revealed on the very next slide. Yeah, sure. So here, instead of doing QAM, if you're just taking BPSK, 1 bit, so your data in bits would be 1, 0, 1, 0. And BPSK simply says, if your bit changes, then change the phase, which is why we get an inversion here, and here, and here. Okay, so this is your S sub BPSK. And then if we chip that with the spreading code where these are produced by your Pseudonoise source, then we are going to be doing extra spreads. So in this case, L equals 3. That is, we have 3 chips per symbol. And so things that were nice and smooth and continuous up here get a discontinuity, or at least a change in phase introduced down here. So I hope you can see that because there's more kind of abrupt things happening in the time domain, that this should cause spreading in the frequency domain, that we're doing more things with faster resolution. So your bandwidth has to increase if you're going to do that. Okay, so here's the magic, and I think that this is I call it magic, but it's awesome how simple it is and how effective it can be. So let's look at the receiver here for the first time. On the receive side, I'm going to look at R of t, which is the received signal that has been chipped again by the same pseudonoise sequence. Okay, so what's important to see is that this and this have to be matched. Otherwise, you're not going to get any data. So our received signal y of t is itself a chipped version of, say, S QAM. Right, so y of t is the noise plus the data times the chipping sequence. And so if I multiply that by the same chipping sequence again, I get this power of 2. And what happens when I square a signal that is always either +1 or -1?
You get a flat line.
You get a flat line that's always 1. I just think that, I mean, like, all right, when I say it out loud, it's really dumb, but it's so cool that that actually works, that if you have the same sequence, it doesn't matter what order the pluses and -1s were, as long as you're using the same sequence, pluses and -1s, you are going to completely cancel any chipping that you've done. That's profound. I hope that everyone appreciates that. I can't gauge the room like I could in the good old days. So let's not neglect the noise, right? Because it's a fallacy to say, oh, look at this thing, it works. Well, what does it do to the noise? That's the real question. So I'm going to call the product of the noise process with the chipping process x of t. And so then our received signal is the thing we sent plus this, if you like, somehow filtered noise. Okay, and so the question is, did we do a good job filtering or a bad job filtering? How noisy is X relative to if we hadn't done anything to begin with? So let's make some assumptions. So if n of t is, well, we've modeled it as additive already. But
Wait, I have a question.
Waiting, go ahead.
So if multiple people are trying to transmit through this channel, they're going to have different codes. But if that signal like interferes in frequency, is it not going to affect one of them?
Correct. So yeah, like we'll get to, so if I can hop ahead here just a bit for 4 slides ahead. We're going to talk about multi-access, but let's go back to here. And so let's say that we had, come on, let's add into this chipping sequence 2 times someone else's data, so S2 of t, in which case this line at the bottom, our received signal, would be my signal times my chipping sequence squared, which we've said is 1, plus your signal times your chipping sequence times my chipping sequence plus the noise. And so this is why you want to choose a code. You want this to be small. You want this to be close to 0. Right, so if you and I pick our codes at random, if the set of codes we're picking from has this property where the cross correlation is 0 or close to 0, then we can try and minimize crosstalk, or your interference with me and my interference with you. I hope at this point you should also probably be suspecting that there's going to be something to do with orthogonality, because everything in this course has been orthogonal this, orthogonal that. And so I want you to want this to feel orthogonal. If 2 codes are orthogonal, then I multiply them, I get 0. So that's going to be the same result that we're going to get here. And there's nothing stopping me from just doing 2 transmitters. We could do an unlimited number of transmitters, provided that we each use our own orthogonal code. Then at the end of the day, if I multiply by my code, then everyone else's signal goes to 0. And we can be transmitting at the same time. We can be transmitting over the same band. And if the codes we choose or have chosen for us in modern telecom, if the codes that we use are orthogonal, then the fact that we're talking at the same time over the same band is nullified. It's super, super cool, in my opinion. Ricardo, I don't know how much of that you got.
No, yeah, that completely answered my question. Thanks.
Okay. Sometimes when I finish answering a question, I realize I've been really enthusiastic. I worry that I didn't actually answer the question. I just went off on a tangent. Okay, but we're good. Anyone else want to follow up on that? Okay. So let's go and talk about the noise again. If we assume it's additive, white, and Gaussian, and I think it's not too much to assume that it's 0 mean. Right? It'd be weird if the RF noise caused drift, like if it had non-zero average. Then both of these together imply that x of t is a 0 mean Gaussian. Because we're only multiplying it by +1s and -1s at any given time. So the result will also be a 0 mean Gaussian. All right, so what else can we say about this? Well, the power spectral density of the X signal, if we're multiplying in time, that means we're going to convolve in frequency. And so what we get is, again, spreading, but since the noise was white at the beginning, then we're spreading something that was already flat, and so the result will also be flat. And so the idea is that this is a kind of a short argument for you to choose your spreading code, your C of t, such that you're taking an additive white Gaussian noise process and making another white Gaussian noise process out of it. This can be accomplished if you make your autocorrelation. So we want the autocorrelation of C to be something like an impulse. This is just a rehash of you'd like them to look like a delta of t minus some integer multiple of the symbol period. Okay, so if you were able to make your autocorrelation have that kind of your chipping sequence have that kind of autocorrelation, then what you would get is you would just get copies of the S of n because you'd be convolving with deltas. And so, I mean, it's not strictly necessary to make this system work, but if you want to analyze your system, it's nice that your spreading code doesn't make the noise not nice. If you follow that line of logic, right? There's a lot of nice properties about additive white Gaussian noise processes, and if you were to disrupt any of those or to lose any of those, but with your chipping process, then it would make the analysis harder. In particular, if you were able to accomplish this, have this nice autocorrelation property in your chipping code, then especially for BPSK, you'd be able to use our old bit error calculation rate, which is the Q function evaluated at the square root of twice the bit energy divided by the the noise power. So remember that this is square root of the bit energy relative to script n over 2, which was the power spectral density level of a white Gaussian process. It's just a callback to stuff we've already worked on, right? Working out bit error probabilities in the presence of white Gaussian noise. If your chipping sequence doesn't make your noise process not white Gaussian, then you can use our old results, is all I'm trying to say. All right. So just like FHSS, DSSS is also JAMA resilient. How we can do this is we'll take a little bit more time and model this a little bit more finely than we did in FHSS. So we're still going to have these kind of weird jelly bean tree things, but we are going to, again, mix our baseband signal with the chipping sequence, which has the effect of spreading out. Hence the name, spread spectrum. And so what we're going to do is we're going to add not a noise process, but an interfering process. So this could be a malicious jammer, or it could just be someone who's transmitting on this band, and they're not out to get you, but they're not looking out for you either. Okay, so what will be a good term for that? Just a neutral interference. Someone just cramping out. What am I trying to say? Pumping out RF energy in your band. That would be this model. So the interferer, if they are concentrating their power right on your carrier signal, what you're going to do is you're going to end up multiplying the received signal, y of t, by your chipping sequence. But remember, your chipping sequence was designed to spread things out. But just because you spread yours out with c of t at the transmit, by multiplying by c of t at the receive, you actually despread your own signal and spread the interfering signal. Which means that once you bandpass filter this, you can go duck, 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 and then you're left with a nice, powerful desired signal and a small interference level. So this is a way to do a little plug and play if you already have a QAM modulator and demodulator. So this is a good opportunity to define a new ratio, a new figure of merit. So far, we've been talking about signal to noise ratio. With which, like, that always kind of bugged me. Like, I get what you're trying to say, but noise is itself a signal. And so saying signal to noise, I don't know, it always kind of bugged me that no one ever says desired signal. I know it's implied, but I don't know, maybe that's on my own hang up. What I'd like to introduce now is an SIR, which has a similar problem. It's a signal, but now instead of noise, it's the signal to interference ratio. And then if you like, you'll often see these actually combined into SINR, which is then a signal to interference plus noise. So the thing you want divided by the other stuff, basically. So in this particular slide, we're looking at an SIR type problem because we've thrown the noise away for now. So if we look at this picture right here, then the SIR in that particular picture would be the energy that you put into the bit. So I guess there's something more that we should talk about. The fact that this and this appear to have the same area is not an accident, right? So the idea is that we're not actually changing the energy because we're multiplying by plus and minus 1. These two have the same area. And if we're talking about power spectral density or energy spectral density, that means they have the same energy or power, depending on which one you're talking about. Okay, and we're just going to call that E sub B. Okay, so in this particular diagram, we've got the ratio, your signal, EB, divided by the power in the interferer, divided by the spread. And the reason that I've defined it like that is because this is before spread. Before D spread and after D spread. The SIR, you haven't changed your signal energy, but you have diluted the interference. So you're taking your old value of PI over BS, and then you're going to divide that by the spreading factor. So I think that I did not originally define this bandwidth. That's what I'm calling BS, or the bandwidth of the signal. So your interferer is going to have his or her power distributed across just this bandwidth. And then after you spread it out, you're spreading it out by like the spreading factor. That's why it's called the spreading factor. You're spreading it out by a factor of L, or L plus 1 in this case. And so this is clearly better, bigger after you despread. Okay. And there are 3 or 4 different knobs and parameters you can fiddle with here. You could fiddle with your EB, you could fiddle with their total PI, you could fiddle with the baseband bandwidth BS, and you could fiddle with the spreading factor L. In all of those cases, the things that you would expect to happen would happen. If you increase your EB, then your SIR improves across the board. If you increase their PI, then your SIR diminishes across the board because you're giving your opponent more power. But if your opponent, if your jammer or your interferer starts to practice what's called broadband jamming, so if they don't just jam a single frequency and they maybe start to do something like this, then all of a sudden they're not concentrating all of their power at a single frequency, but they're pre-spreading it for you. And so when you despread it, what you can actually end up doing is mixing in adjoining bands and actually contributing to your own downfall. So you're not going to ever be worse off than if you didn't despread, but the factor of L plus 1 improvement that we see here, that diminishes, that improvement factor diminishes if your interferer, him or herself, is transmitting over a spread spectrum. Okay, and so that's the phenomenon. This dashed line is something called broadband jamming. Again, there's not a whole lot you can do to combat that. One choice that you could make is switching to FHSS, in which case you're not despreading, you are just hopping between frequencies, and therefore at any given frequency you're seeing a diminished power from the jammer because the jammer then has to spread his or her power out over more frequencies. So this, to combat about broadband jamming, you might consider doing something, I won't say worse, but certainly an older technology, which is FHSS. Okay. I think that's a good place to stop because the next topic is CDMA, which stands for Code Division Multiple Access. And this is the kind of the unsung cousin of TDMA, Time Division Multiple Access, and FDMA, Frequency Division Multiple Access. We now have CDMA, that is, you can divide users of a common physical channel by code instead of by frequency band, instead of by time duration. So CDMA played a major role. It was the technology du jour for 3G mobile telephony. But once we were able to get FFTs fast enough to facilitate OFDM, that's why we switched away from them. That's why the tech was switched from CDMA in 3G to OFDM or OFDMA in LTE. Okay, but yeah, we will talk about CDMA. There is a huge setup here and a lot of arithmetic waiting for us, but don't let that dissuade you. I'll see you on Wednesday.